Hello and welcome to the AICE Chemistry lecture series. In this video we're going to look at the reactions of the halide ions, not the halogens as in the diatomic molecules, but the reactions that compounds that are ionic and contain a halogen ion or a halide ion are going to undergo. So let's get started. Now, the first thing we're going to learn is how to test for halide ions. This is a skill that's going to be absolutely necessary for paper 3 and the qualitative exam that is in that paper. We can identify the three most common halide ions, which are the chloride ion, bromide ion, and iodide ion, with a very simple test. The test consists of adding dilute nitric acid first, which is going to have the same anion as our next chemical. And that's going to acidify the solution and get rid of some of the ions that might be in there that are going to interact with our test. And then once we have the nitric acid, we're going to follow that up by adding silver nitrate, aqueous silver nitrate, to the unknown solution. What's going to happen here is if we have a positive result, if there is a halide ion, chlorine, bromine, chloride, bromide, or iodide in there, we're going to get a precipitate, and depending on the halogen that we have in there, we'll get a different color precipitate. What's happening here is that the silver nitrate itself is reacting with the halide ion and creating in essentially what is a double replacement reaction, the silver halide. X here is used in a lot of cases to replace a halogen ion in a generic equation. So here X could be any of the halogen ions. X could be Cl minus, it could be Br minus, or it could be I minus. So what's going to happen is the halide ion is going to replace the nitrate in the silver compound, creating the silver halide, which all three silver halides, AgCl, AgBr, and AgI, are all solids. They're not soluble in water. So because this creates solids, we are going to see a precipitate if we have a halide ion. The nitrate ion stays around and just floats around because the nitrate is very soluble in water, but the silver halide will precipitate. So if we get a precipitate in this reaction, that is a positive test for the halide ion. Now there are two ways to identify the halide ion. One is more vague and not as accurate. One is a lot more accurate. When we get that precipitate, the precipitate will be different colors depending on the halide present. Silver chloride that forms when the chloride ion is present is a white precipitate that we see in this picture right here. Whereas silver bromide, where you form with the bromide ion, is going to be a cream color precipitate. So you can see here in the middle, you can tell this is not a very distinctive precipitate color, right? White, cream, they're very close to each other. Iodine is a little better. Whenever iodide ions are present, silver iodide is formed, which is a pale yellow precipitate. So we can see that a little more clear here in this picture. The AgI is has more of a yellow color. But these three precipitate colors are not extremely distinctive. They're not easy to see to the naked eye. Obviously, when we see them here and we compare them next to each other, it's a bit more clear. But if we were to do this and only have one of these, so if we only have, for example, the AgBr, could you really tell that the AgBr was AgBr from looking at it and not AgCl? I mean, they're both just off colors of white. So how do we go about actually figuring out which halide do we have? We do a test with ammonia. So you see, what happens is that the silver chloride is insoluble in water and forms a precipitate. But if we add a little bit of ammonia, if we dissolve that into dilute ammonia, that silver chloride will dissolve. And by dilute ammonia, we mean we add a few drops of ammonia to the precipitate. We add a few drops of ammonia to the silver chloride, and it will dissolve. Whereas the silver bromide and silver iodine will not. Silver bromide will, however, dissolve when concentrated ammonia is added, meaning when we add a large amount of ammonia. And so the silver bromide, the cream precipitate, will be soluble in concentrated ammonia, whereas the silver iodine, the pale yellow precipitate, is not soluble in any. So let's look at how we would look at this test in a more clear picture. So what we will do is, if we have 3 samples, for example, one of each ion, or if we're just testing a sample, we will first acidify that solution by adding nitric acid, dilute nitric acid. Now, at that point, we're not going to see any changes in that solution. What the nitric acid is doing is acidifying the solution so that it prevents unwanted precipitates from contamination. After we add the nitric acid, we are going to then add that silver nitrate. When we add the silver nitrate, if we did not have a halogen or a halide ion, we wouldn't see a precipitate, we wouldn't see any change. But if we had chloride ions, like in sample A, we will see that white precipitate. If we had bromide ions, like in sample B, we will have a cream color precipitate. And if we had iodide ions, like in sample C, we'll have a yellow precipitate, pale yellow precipitate. But again, these colors are not as distinctive as they are in this picture, so how can we tell? Well, we will first do an aqueous ammonia test, a dilute aqueous ammonia test, meaning we will add a few drops of ammonia into our test tubes. The chloride sample, the one with silver chloride, would dissolve. It would turn into a colorless solution because a silver chloride would form a complex, which we'll study in A-level chemistry. And it will dissolve in that few drops of ammonia, that dilute ammonia. If we do the same thing to the silver bromide or the silver iodide, we would actually see no change. That precipitate wouldn't go anywhere. So that's the first step. But if it dissolves, we know we have silver chloride. And that was a chloride ion in the sample. If it doesn't dissolve, that's not where the test ends. If the samples don't dissolve, we are going to add concentrated ammonia. And how do we add concentrated ammonia? Well, we just add a large amount of ammonia to our test tube. And if it dissolves after adding a large amount of ammonia, and we concentrate the ammonia, we know that that precipitate is silver bromide. So our original sample had the bromide ion in it. And if it doesn't, if that precipitate stays even after adding a high concentration of ammonia, then we know that it was iodide ions in the sample, silver iodide. So this is what is known as the silver nitrate test for halides. And it's a very common test that you'll probably end up performing during your paper 3 examination for the AS chemistry exam. So do keep this in mind, it's a very common test. Now, this is how we test for the halide ions. But what reactions can the halide ions form? Well, the reactions are mostly due to their reducing power. Halide ions are going to be reducing agents, which means that they in general will want to lose electrons and become the halogen ions, or the diatomic halogen, should I say, that they originally were. In general, there is a trend to the reducing power of the halide ions. Chloride is the least reducing of the 3 halides. And again, we're not looking at fluoride because it's not as commonly seen, but chloride is the least reducing of the halide ions that we have here, and iodine is the most reducing. And that's because the reducing power of the halide ions, their ability to give electrons to other chemicals, is going to increase down the group. So as we go down from chloride to bromide to iodine, the reducing power, which is the ability again of the halide ion to lose electrons, give them to something else, and become the halogen molecule, and again this X just represents one of the halogens, is going to increase as we go down that group. The reason is very simple. It's a reason we've studied a million times, both in chapter 10 and before that, in the early chapters. As we go down the group, two things happens. The radius size of the ions increases. From chloride to bromide to iodide, we gain an extra shell energy level. Chloride is in period 3, so it has 3 energy levels. Bromide is in period 4, so 4 energy levels. Iodine in period 5, so 5 energy levels. Well, as we go down, because the ion is bigger, there is more shielding from those inner electrons as we add those energy levels. The attraction between the nucleus and the outermost electrons, because of that, becomes much weaker, as well as because the distance increases. So both the distance and the shielding increase as we go down the group. And that makes it easier for that element to lose electrons. So iodine can lose electrons a lot more easily because it's much larger with much more shielding, which is preventing these outer electrons from feeling the full force of that nucleus. This is very telltale sign of how reactions are going to go with the halide ions as we go down. The reactions, which are redox reactions of the halide ions, are going to become more and more drastic. And that's because as we go down the group, the ion itself, the halide ion itself, becomes a stronger reducing agent. It has more reducing power. The main reaction we're going to see this in is the reaction of the halide ions, usually in either potassium or sodium halide, with sulfuric acid. So let's look at those. And we're going to go one by one. First is a reaction of the chlorides, like sodium chloride or potassium chloride, with concentrated sulfuric acid. Chloride ions are, like we just said, not the strongest reducing agents, so they're not able to reduce the sulfur in sulfuric acid. Chloride ions have the smallest radius and the least energy levels, and so they're not very strong reducing agents, which means that they cannot reduce the sulfur. So when sodium chloride reacts with sulfuric acid, we don't get a redox reaction. We actually get what essentially is an acid-base reaction or a double replacement reaction. The reaction is carried out very simply, and all of these reactions we're going to discuss in the next few slides are carried out by this, where we have a solid sample of the sodium chloride, and then we are going to slowly drop sulfuric acid, concentrated sulfuric acid, onto it. So the sodium chloride or the potassium chloride, which is I think we do this experiment with, or this reaction with, is going to be solid, and then liquid sulfuric acid is dropped onto it. And what is going to happen is that the sodium and the hydrogen are going to switch places essentially, by only one of the hydrogens, creating hydrochloric or hydrogen chloride gas and sodium bisulfate, NaHSO4. The NaHSO4, the sodium bisulfate, is going to stay solid, and the hydrogen chloride is going to come out as a gas. That's why it's important for this reaction to happen with a solid sample of sodium chloride with the liquid sulfuric acid. It allows, because there's no water present, it allows the hydrochloric acid to come out, the hydrogen chloride to come out as a gas instead of dissolving and creating hydrochloric acid. And usually we'll do this in a way that we can then, that gas goes through a tube and we can collect it in another container. So what are we going to see when we drip concentrated sulfuric acid onto sodium chloride or potassium chloride? Is we're going to see steamy white fumes. Those steamy white fumes being hydrogen chloride. Again, this all happens because the chloride ion is not a strong reducing agent. Since the chloride ion doesn't oxidize or reduce the sulfur or anything at all, what the reaction is considered to be an acid-base reaction, and the oxidation number of sulfur doesn't change. The oxidation number for the sulfur in the sulfuric acid is +6. When we look at the product side, the oxidation number of the sulfur in the bisulfate ion is also +6. So there's no change here in oxidation numbers, and therefore there is no redox reaction when the chlorides react with sulfuric acid. But that's not the case with all halides. Let's look at the next one. Let's look at bromine, or bromide, should I say. Reactions of bromides with concentrated sulfuric acid. Bromide ions are stronger reducing agents than the chloride that we just saw. And because they're stronger reducing agents, they're able to not just undergo the first step, that acid-base reaction we discussed, but they are actually able to undergo a second step where the bromide ion acts like a reducing agent with sulfuric acid. So, in the first step of this reaction, just like with the sodium chloride, the sodium bromide, which is a solid, is going to react with the sulfuric acid to create the sodium bisulfate and AgBr gas, just like it did with chlorine. This reaction is a parallel of the chloride reaction. But a secondary reaction also happens. Once that bromide is created, it then reacts with the sulfuric acid that's present that we're dropping onto this mixture. The HBr created in this reaction then has a secondary redox reaction with the sulfuric acid. The bromide ions act as a reducing agent where they reduce the sulfuric acid, the sulfur in the sulfuric acid, into sulfur dioxide. So this reaction creates three things. It creates sulfur dioxide, bromine gas, and water. Now this is a redox reaction because the sulfur, like we said in sulfuric acid, has a +6 oxidation number. In the sulfur dioxide, the oxidation number of sulfur goes to +4. So you can see how we go from a +6 to a +4 oxidation number on the sulfur, indicating the reduction of sulfur. On the other hand, we also get the oxidation of the bromine, or the bromide, should I say. Bromide goes from being -1 in the hydrogen bromide to 0 in the Br2. And that indicates the oxidation of the bromine. So we have the reduction of the sulfur and the oxidation of the bromine, which is why this is classified as a redox reaction. And this is due to the HBr minus having more of a reducing power, a stronger reducing agent, than the chloride ion, because of the factors that we discussed earlier, shielding and size. Now, as far as the observation is very clear in this reaction. Because we create bromine gas. Bromine gas has a very distinctive reddish-brown color. So when we drop this, at first we're just going to get a bit of a steamy white fume from the HBr, which is not the main observation in this reaction. Instead, once we drop enough of that sulfuric acid, we won't get the steamy fume that is HBr. Instead, that will transition into a red-brown gas. That is the main observation of this reaction. We will also smell a choking smell. That's the sulfur dioxide that's being created. It has a bit of the smell of a burnt match. So we can see that here. The bromine gets oxidized from -1 to 0. The sulfur gets reduced from +6 to +4. And that is the reaction of the bromide. It's like sodium bromide, or it could be potassium bromide, with sulfuric acid. And that's all because of its reducing power. But there's one more halide that has even more reducing power than the bromine, and that is iodide. The reaction of iodide with concentrated sulfuric acid is even more drastic. Iodide ions are the strongest reducing agent out of the common halide ions. And that's again because they're the largest with the most shielding. The reaction is going to happen in two-step, just like with bromide, but that second step has 3 different variations. So step 1 is the same. Step 1 is the sodium iodide or potassium iodide, depending on what you're reacting with the sulfuric acid, which is being dropped onto it, and creating the sodium bisulfate and hydrogen iodide gas. Now, what's going to happen here is that hydrogen iodide is going to then go and react with the sulfuric acid. Now, this can happen in 3 ways, and it's not that it will happen in one of the 3 ways. All 3 of these will happen to different molecules of HI. So one HI might undergo this reaction, the next HI that's created might undergo this reaction, the HI that's created undergoes this reaction. So we get a mixture of all 3 reactions going on at once. The first reaction is essentially the same one we saw with bromide. The HI reacts with the sulfuric acid, creating SO2 on water, but in this case creating I2 gas, the iodide gas. Iodine, sorry. The other reactions are further oxidations further reductions of the sulfur. In the second reaction, the hydrogen iodide reacts with sulfuric acid. It still creates the iodine gas. It still creates water, like they all do. They all create iodine gas and water. But the sulfur gets reduced all the way to solid sulfur. And then in the last one, the reduction goes even further with, again, the HI and the sulfuric acid reacting, creating iodine and water, but the sulfur getting reduced all the way into H2S gas. So if we look at here the oxidation numbers, again, the oxidation number of the sulfur in sulfuric acid is +6. But in SO2, it will get reduced to +4. If the reaction is that creates S, the oxidation number gets reduced to 0. And if it's the last one, it gets reduced all the way to -2. So all 3 of these are the reduction of sulfur, but into 3 different compounds with 3 different oxidation numbers for sulfur: +2, +4, 0, and -2. So it's a very interesting reaction because what happens here is that we don't get one reaction, we get 3 reactions all going on at once. And because of that, we get a lot of different observations. We get a purple gas from that iodine vapor. That I2 gas is very deep purple. We get a yellow solid from the elemental sulfur, from the sulfur solid that's created. And we get hydrogen sulfide gas, the H2S gas, which has a rotten egg smell. So that's not necessarily an observation because we don't see it, but we do definitely smell it. That rotten egg smell from the dihydrogen sulfide gas, H2S. So this shows you just how strong of a reducing agent iodide ions are. They don't just reduce sulfuric acid into SO2 like bromine, or into just not even reduce it like a chloride. It actually reduces sulfur in sulfuric acid so much it causes 3 different redox reactions with increasingly more negative sulfurs, more reduced sulfur. And so we get this very wide variety of different observations. So this is the main reaction that we learned that we are going to use in order to look at the reducing power of the halide ions, what their reactions with sulfur or sulfuric acid tell us. Chloride does not reduce the sulfur at all, it just creates an acid-base reaction. Bromine reduces the sulfur with, actually let me go back, so chlorine, the chloride ion, just reacts to make the bisulfate ion and hydrochloric acid or hydrogen chloride gas. So no redox reaction here because it's the least reducing power. The bromide ion, which has the second most reducing power, will undergo the same acid-base reaction, but then undergo also a redox reaction to create the bromide gas and sulfur dioxide, the least reduced form of sulfur. And then the iodine, which is the strongest reducing agent, is going to do the same acid-base reaction, creating the sodium bisulfate and hydrogen iodide gas. But then the hydrogen iodide gas is going to undergo 3 different redox reactions, all with increasingly more negative sulfurs, SO2, S, and H2S, which gives us a wide variety of observations. And that's it for section 3. I will see you all in our next video.